Hello everyone. So my name is Muhammad Nasser and I'm a mechatronics engineer from the German University in Cairo. And this is going to be the first video in a series of videos about power electronics. So let's dive right in. So what is power electronics? Okay, so power electronics is a field that has to do with converting some sort of unregulated input power, electric input power. So this is unregulated. For example, the power you'd get from a power station, so your 220, or depending on your country, basically 220 volts AC. And we take this power and we modify it in one way or another. We can say modify, we can say regulate, we can say change its form. There are multiple definitions for this using some sort of device, and turn it into another form of power, which is our output power. So this output power is nothing but a modified form of the input power. It's a modified form or regulated form of our input power. And the reason we do this is so we can run some sort of application. So we run some sort of application in a desired manner. Now this application can be various applications or a multitude of stuff, like for example your DC home appliance. So your DC home appliances. And if you think about it, your DC home appliance, it's taking in an input power of for example, 220 volts AC, and some way or another returning this 220 volt AC into, for example, 12 volt DC. So what we're doing here, we had AC input power and we transformed it into DC output power. And hence we actually changed the form of our power. So what we're doing is we're modifying our power one way or another. And the method we do this is using what we call a power electronic converter. Now there are various forms of conversion. For example, we can change from AC to DC, and usually we'd call this a rectifier. And now these are just some really common applications or terms in power electronics. And we can, for example, change from DC to AC, and we call these inverters. And then we have DC to DC, which we usually just call DC to DC converters. There are other terminologies for them, and from AC to AC. Now, I'm not going to go into any more details, but these are just some basic ideas on what we can do in power electronics. I'm going to actually start this off with a simple example. So let's say we have a voltage source over here, and this voltage source is now connected to some load, which we're going to define by this load resistance. And this load resistance has some sort of output voltage on it. I'm going to connect this. Now, let's say we short circuit this path now. So what's going to happen is if we do KVL, we're going to see that our output voltage is simply going to be 9 volts. Okay. Now let's just say, for example, this is a motor, for example. Okay, so it's a motor. Now, without diving into any details about motors, we can just say if we decrease the voltage of the motor, we can decrease its speed, and if we increase the voltage, we can increase its speed. So this is an example of an application we can actually use bioelectronics for. And now, let's say we want to decrease the output voltage. So we want to decrease the output voltage from 9 volts, for example, let's say to 3 volts. So what we need to do is we need to somehow decrease this output voltage. Now, one method of doing so can be by adding some sort of resistance in series. For example, this can be a potentiometer, a variable resistance basically. And if we set this resistance to 2RL, which is basically twice the load resistance, we can say there's going to be some sort of voltage drop on this resistance, because when we add this resistance, we're going to have some sort of current flowing in, and this current is going to cause a voltage drop over the resistance, meaning that our output voltage is also going to decrease. And now let's do the math. The current is going to be 9 volts over the total resistance, which is going to be 3RL. And the voltage drop is simply going to be I multiplied the resistance. And this means that V drop is just going to be, you got RL is going to cancel with RL, so you get 2 over 3 multiplied by 9, which is going to give you 6 volts. So this is the voltage drop. Now, if we apply KVL once more, the summation of voltages in the loop is equals to 0. We're going to end up getting that V output is now equals to 3 volts. Now this, I guess you can say, is an example of a power electronics application. However, this circuit is not really used. Now let's think about it. This circuit, first of all, is very convenient to use. It's very easy. All you have to do is just move a potentiometer, and you get the required output voltage. And you're converting DC into another form of DC in a very clean or smooth manner. However, it's also cheap, obviously. However, there is a significant disadvantage here, and sorry about that. So this disadvantage is the power loss. So this circuit is not very efficient. And let's take a look. So first of all, what is the input power we're supplying? Now, the power in general is, in the simplest form, is just voltage multiplied by current. Okay. So the input power is just going to be the input voltage multiply the current going in the circuit. Since this is a circuit that was with all its components connected in series, so they all have the same current going through them. And this means that the input power is simply 9 volts multiplied by the current. Okay. Now, what is the output power? Well, the output power, or basically the power being absorbed by the load, is simply going to be the voltage drop on this load, which is V out, multiplied by the current. Now, when we added this resistance, we notice that V out is a third of V in. And what this means is, it means the money we paid for here, which was 9 volts multiplied by the current, which is, I'm just going to call it V in multiplied by the current, we're only utilizing 33% of it. So if we're paying $10, for example, we're only getting $3.33 out of our money's worth, basically. Uh, and this is pretty bad. Now, if you think about it, now don't think about it as $10 or some sort of simple application you're running at home or some Arduino and such. Think about it as economy for an entire country. For example, you're talking, for example, a multi-billion dollar, multi even trillion dollar industry. If you think about all the application that uses electric circuits in the world. And what you're saying is, if we were to use a circuit like this to control the output voltages on all of our loads, for example, instead of a multi-trillion dollar industry, we would need to pay that same amount of money but multiplied by 3 in case of this resistance. Now, imagine if we even increase this resistance even more, 5RL, 10RL, and so on. The efficiency is going to keep on dropping as we increase the resistance more and more. And so the efficiency keeps on dropping, and resistance keeps on, as we increase the resistance, means we're going to keep on making even more and more money. And now there's even a second disadvantage here. It's actually quite critical, and that is any current or any power being lost over this resistance is transferred into heat in the end of the day. Any power loss over any resistive load whatsoever, not just in electric circuitry, even in mechanical systems. If you have some sort of damper to act as some sort of mechanical resistance, you're going to end up having heat transfer, or basically you're going to have heat being generated in this resistive component. And this heat can easily damage our components. And in electric circuitry, if you think about it in a PCB, for example, you have so many components beside each other, so adding a simple resistance over here can easily damage these components. It can raise their junction temperature, and once that happens, your circuits get fried, basically. So if you use this method, you're going to need some even efficient method of cooling as well to make sure that your system does not get damaged. So overall, this is a very bad manner of converting power, or basically manipulating power to be more precise. And now, the second way of doing so, or the second example that I'm going to show you here, is going to be the same circuit. However, and this is the same load with resistance RL. However, we're going to add some sort of switch here. And now let's discuss the properties of this switch. In this case, it's an ideal switch. So the properties of an ideal switch is the following. When it's open, it has a voltage drop on it that's equals to V open circuit. However, it has zero current. And this means that the power consumed on the switch is zero, because you have voltage multiplied by zero current, that means zero power. Now, when the circuit is turned on or closed, you have a closed or short circuit, basically. And what this means is the current going through the circuit is the maximum amount of current possible, which is I short circuit. However, it has 0 voltage on it. And so the power is also 0. And the nice thing about an ideal switch is that it basically consumes no power. And so let's use this ideal switch here to manipulate our output voltage. And now let's say now we turn on and off the switch repeatedly. So what's going to happen is, and this is going to be a function of the output voltage with time. Once we turn on the switch, we're going to have an output voltage of 9 volts. And once we turn it off, we're going to have 0 output voltage. And now if we keep on repeating this sequence over time, we're going to keep on getting this waveform which has some period capital T. And the time we're on, or the time we close the switch for, is going to be T on. And the time we're going to be closing it off for is going to be T off, and T on plus T off are just going to give us T. And now the ratio between T on and capital T is what we call the duty cycle. The duty cycle is simply a percentage, I guess you can say, of how long our circuit is on, or basically for how long are we going to have a positive output voltage, I guess you can say. And now let's analyze this output voltage waveform here. So to analyze this output voltage waveform, sorry, I inserted the beige above and not below. So to analyze this voltage waveform, what we have to do is we have to get its average. Now the average of a voltage or of any function basically is going to be 1 over the time, the integral from 0 to set time, the function, so let's say for now it's a function of time, dt. And what this does is, it simply says, you have some function here, and it can look like whatever, and this is some time t. The average is, what the average says is, you're going to calculate the area under this waveform, and divide it by the time that you calculated this area for. And for the voltage, is going to be the exact same thing. However, since in this case our voltage is periodic, then we only need to calculate the average for one period t, because the average is going to be the same for all the other periods, since it's basically a copy paste of your voltage being repeated over time. And we go over here and actually do the math. We can say that V average is simply 1 over the period, the integral from 0 until the period, this voltage as a function of time dt. So this is the average component of your voltage. And if we do the average component for our voltage waveform here, we will notice that it has a value from 0 up until t on. However, it's 0 everywhere else. So we only have to do this integral from 0 to t on. So you get 1 over t, the integral from 0 to t on, the input voltage, which is basically a constant number. And so you end up getting V in multiplied by this duty cycle, which is T on over T. And if we pay close attention here, we notice that depending on how long we keep our circuit or our switch on, we can control our output voltage. And allow me to be more precise, we can control the average component of our output voltage. Now, a nice way of thinking about the average component of an output voltage is just basically some straight line over here. And this straight line has the same area under it as this on period. So if you calculate the area under this straight line, or this average component, should be the same as the area under this high voltage component. And someone might obviously argue, but hey, this is still not the same as, for example, having 3 volts. So basically, only turn the circuit on for 33% of the time. So if we only turn the circuit on for 33% of the time, so best way to describe this is as D is equals to 33%. It's still not the same as having an output voltage of 3 volts. What you're saying is that the average component of your output voltage is 3 volts. Well, yes, that's true, but what you can do here is you can use this circuit, and this is our 9 volts, and pass it by what we call a low pass filter, for example. So this is a low pass filter. And a low pass filter is basically a filter that passes by low frequencies. So it allows low frequencies to go through, and for high frequencies, it's going to make their magnitude, or it's going to attenuate them, basically making their magnitude almost equal to zero. So by allowing only the low frequencies to pass, we can easily allow our DC component to pass and then feed it to our source. I mean, feed it to our load. Sorry about that. And this is usually what we do in real life applications. Now, obviously, the switch here is not going to be ideal, and this filter here is going to have some losses, because filters are basically composed of electric components, and that means they're going to have some loss of some sort. But regardless of how much losses we have in our filter or how much losses we have in our transistor, I'm sorry, in our switch, which is usually implemented using a transistor, uh, whatever the losses may be, it's still going to be a lot better than when we were using the resistive method. If you notice, the resistive method had only a 33% efficiency. This resistive method only 33% efficiency. And like I said, for example, if you do 10 RL, 11 RL, 12 RL, the efficiency is going to even drop even more north to 5%, 4%, and so on. And hence, this method of using the switch and basically opening and closing the switch in a desired manner to give us a desired output power is much more efficient. And really, this is what power electronics is. Okay, so what power electronics is, it's at the end of the day, we have a bunch of switches, and we're closing and opening those switches in a desired manner. You could have multiple switches in barrel, for example. Some designs might have switches in this form, for example. And you have some input voltage here and output voltage here of some sort. So there's a lot of switches you can, or schematics you can use at the end of the day. The way you turn those switches on and off, the way you arrange them and organize them, you can easily manipulate your input power. And I'm just going to use Simulink to show this to you in a practical manner. So this resistance, I'm going to make it 2 ohms. This load resistance I'm going to make 1 ohm, and this is the output voltage, 9 volts. And over here, we're going to, this is our ideal switch, and we're gonna set it on a period of 1 millisecond, and we're going to give it a pulse width of 33%, and this is also 9 volts. Okay, I'm going to run this circuit or this simulation. Obviously, this is just a simple KVL, the one on top. You don't really need a Simulink to imagine the output's going to be obviously 3 volts, as you can see here. And in this case, we're going to get this nice voltage waveform I've shown you before. If we zoom in, we notice that for one period, we're on for 33% of the time, and we're off for the other period of time. And if we use some sort of low pass filter here, we should be able to see our voltage converging to 3 volts. So as you notice, we're getting closer and closer to 3 volts. Now obviously this depends on your low pass filters and the parameters used and such and so on. However, as you can see, you can still get an output voltage of almost 3 volts. For example, let's make this pulse width 50%, so we're expecting an output voltage of 4.5 volts. And if you look here, we see that our output voltage is indeed very close to 4.5 volts. Now let's say, for example, we want to calculate the power loss. So what we can do is we can get a current sensor here, okay, and a voltage sensor. Actually, we're just gonna make this a constant of 9 volts, since our voltage is always going to be constant since it's a DC voltage. Let's connect this current sensor here, and let's multiply those two values together. Okay, so this is the power supplied by our source. It's simply the current multiplied by the voltage. And we will be doing a very exact same. We have a product in our output. So this is the output voltage multiplied by the very same current. Since it's a series circuit, so the same current runs through both of them. And we run the circuit again. So you can see this is the power consumed. It's 80 watts for this period of time, and then it goes to 0 because the circuit turned off. and over here it's the very same waveform. Now, similar to how we did with the voltage, you can also calculate the average power, and it's the exact same. The average power is just 1 over the period, the integral from 0 until the period of your power as a function of time, obviously, dt. And like I said, this average waveform or this average formula really applies to any periodic function. Now, if it's not a periodic function, then obviously it's not going to repeat itself every period t, and so you're going to need to do it to some sort of time t small. And obviously, as the time changes, the values are going to change and so on. But regardless, as you can see here in this circuit, we have a power efficiency of 100%. Now, in reality, this switch is not going to be ideal. We're going to have some sort of losses on it. However, this will be discussed in the next video. Now, before I end this current recording, what I do want to say is that this course or these series of videos are going to depend on a textbook called Power Electronics by Daniel W. Hart. The examples, the content, and so on, I'm just going to be getting it from there. And I would recommend you do read this textbook. I think it's a really nice textbook. Obviously, there's a lot of textbooks around. All of them are really good. Um, Textbooks are really just a matter of personal preference. In my opinion, I just really like this one. It keeps things a little bit simple and at the same time gets the the general idea going to you in a correct manner. So anyways, the next video is probably going to be about switches, and to be more precise, transistors, diodes, and thyristors. So basically, we're going to talk about how we can implement those ideal switches, which we are going to use from now on in our power electronic converters. Thank you for listening. This was Muhammad Nasser, and see you guys in the next recording.